Hello class, today we are starting Chapter 10, which is all about radical functions and geometry. Section 10.1 focuses on square root, aka radical functions. By the end of today's lesson, you'll be able to graph square root functions using a table, identify the transformations of square root functions, and be able to find the domain and range for those functions. Starting off, a square root function is an equation that contains the square root of a variable. So that means our variable is inside that square root symbol. The radicand is something that we are going to use throughout this entire chapter, and that is an expression underneath the radical, aka the square root sign. Any values that make the radicand negative are excluded from the domain. So any x's that we plug in that make that square root turn into a negative number are not going to be part of the domain. So last chapter when we were dealing with quadratic functions, our domain was always all real numbers. For these square root functions, the domain is going to be different. It's not always going to be all real numbers. Looking at the parent, or the most basic function for the square root function, we have f of x, or y, is equal to the square root of x. So if I plugged in those points into the calculator, I would get 0, 0, 1, 1, 2 at 1.41, 3, 1.73, and 4, 2. So we get that nice curve that's going along this line. Looking at the domain of this function, if you tried to plug in -1, it would say square root of -1. We know that isn't possible, so the smallest number that we can plug in is 0. So our domain is x is greater than or equal to 0. The range is going to work the same way, looking at those y values. The lowest possible y value we can get is 0, so we are greater than or equal to 0. When you are looking at these functions, your domain and range are going to be directly dependent on this starting point. So wherever that graph starts, that's going to give you the values for domain and range, and you're going to have to decide, are you getting greater than or equal to or less than or equal to those values. So now we're going to switch the graph a little bit, and we're going to have 2 square root of x. So you're going to plug that into the calculator and go ahead and make the table. Again, we can't plug in negative values, so we're going to start with 0, 1, 2, 3, and 4. Plugging those into the calculator, you get an answer of 0, 2, 2.83, 3.46, and 4. Putting these on the graph, you're going to get the shape, 1, 2, 2 is at 2.8, 3 is at roughly 3.5, and then 4. You're going to connect these with a smooth curve, and that's going to be your graph. Looking at the domain, our starting point hasn't moved, so the smallest x I can plug in is 0, so we're at greater than or equal to 0. The range, y is also greater than or equal to 0, since our y values are getting bigger than that number. Go ahead and try graphing this one on your own, finding the domain and range. Following is your table. I counted up by 2's to make sure that the graph fit. Domain, once again, is x is greater than or equal to 0, and the range is y is greater than or equal to 0. Now we're going to look at the actual complex version of the equation, which is y is equal to a square root of x minus h plus c. A lot of times you will see this x minus h in parentheses. That value is underneath the square root. The plus c is not. So what do these different things tell us about the equation? First, looking at this a value out front. If there was a negative, we were going to ignore it for the minute. So that's why it says absolute value. So we're just looking at the value, not whether it's positive or negative. So if the value of a is bigger than 1, that's going to stretch the graph out. So instead of curving like this, our new graph would curve higher up. So that original graph would be the bottom. If there's an a value bigger than 1, that new graph is going to be stretched up top. Opposite of that, if it is less than 1, we're going to call it compressed. So if our original graph was this line right here, our value, if it was less than 1, is going to be going below that or getting pushed down. Then we're going to pay attention to if a is positive or negative. If it is positive, there is no reflection. And if it is negative, there is a reflection. So again, if we think about the original graph, if it looked like that, the new graph would, if I have not a reflection, would stay exactly the same. If I have a reflection, it would be the same graph, but flipped upside down. The C value, that's what tells us how it moves up and down the graph. So if C is positive, you are moving up C units on the graph. And if it's negative, you are moving down C units on the graph. So if it's positive or addition, you're going up. Negative with the subtraction, you are going down. Last, if you see minus h, so if you're subtracting an h value, that is going to move you h units right. So you are moving h units to the right if you are negative, and if you are positive, you are moving h units to the left. I know that seems a little backwards, but think about if you are plugging in a point. If you are plugging in a value that is negative, aka moving to the left, you're going to have minus a negative, which would turn into that positive value. So if you're going to the left, aka moving negative, you're minusing a negative, which is subtracting. And if you have a negative h, that means you are minusing a positive, which is going to leave it as the subtraction. So now, looking at this graph, it wants us to compare with the parent function and as well as state the domain and range. So again, we're going to start our graph by looking at what we can plug in. So I can start with 0, 1, 2, 3, and 4. When I plug those values in, I'm going to get 0, negative 3, negative 4.2, negative 5.20, and negative 6. So plotting that on the graph is going to give me a curve that looks roughly like this. And then we need to compare with the parent function and state the domain and range. So looking at the comparison, we have an a value. So that 3, which is greater than 1, is going to tell us that it is stretched. The negative tells us that there's a reflection. There's no addition outside the parentheses, so we're not moving up or down. There's no addition in the square root or out of the square root, so we're not moving up, down, left, or right. Then for the domain and range, our domain, x is in this case still getting bigger than 0, so our values on the x are still getting greater than 0. But for our y values now, we have y is less than or equal to 0. Those are going below 0. One more example of this. Again, we're going to start with our table. If I plugged in 0 to this equation, 0 minus 1 would give me a negative 1. So I can't start with 0. So I'm going to start with 1. 1 is the smallest thing that I can plug in to get a positive value. So 1 minus 1 is 0. So that is my starting point for my table. So 1, 2, 3, 4, and 5. Plugging in those values, I'm going to get 2, 2.5, 2.71, 2.87, and 3. Again, coming over to the graph, I'm going to start at 1, 2, 2, 2.5, 3, 2.7, 4, 2.8, 5, 3. Going ahead and connecting these points to get my graph. Now I want to go back and look at how it changes. That 0.5 is less than 1, so that tells me the graph is getting compressed. It is narrower than it was to start. There's no negative out front, so there's no reflection. Then I've got plus 2, so that tells me up 2 units. And I've got minus 1, so that tells me right 1 unit. Then looking at the domain and range, the smallest x value I could plug in was 1. So I'm going to say x is greater than or equal to 1. Then I'm looking at my range. The smallest y value I got was 2. So y is greater than or equal to 2. Go ahead and try this one on your own. We have our table. 0 and 1 did not work. We start at 2 then. After we look at the graph, we see that it's up 2 and right 1. Domain x is greater than or equal to 2, and the range is y is greater than or equal to 1. If you have questions about this or anything else from the lesson, please let me know when you get to class.